In Chapter 14, we're going to take a look at intermolecular forces. So forces that occur between molecules are intermolecular forces, and one of those forces is called a dipole-dipole force. There are hydrogen bonding that happens within a dipole-dipole force. We have London dispersion forces as well, and we're going to go through each one of those today. This is the interaction of two polar molecules. Remember, polar molecules have an unequal sharing of electrons, just like a water molecule does. So it's going to pull this end, is going to pull the electrons more of the time, making this end positive. And that positive, slightly positive end is going to get attracted to the slightly negative end of another molecule that's around it. So this tries to show you what the attraction would be between negatives and positives, and between positives and positives, or negatives and negatives, you would see repulsion. That happens when they're in a liquid form most of the time. So a dipole moment, these are molecules with polar bonds behave as an electric field as if they had a center of positive charge and a center of negative charge. The molecules with dipole moments can attract each other electrostatically. They line up so that the positive charge and the negative ends are close to each other, just like in the picture on the previous slide. There's only about these dipole-dipole forces are a force to be reckoned with, but they're not as strong as an ionic or a covalent bond. So it's not a true bonding, but it does have an effect on the molecules around it. Hydrogen bonding is a strong dipole-dipole force, and hydrogen is bound to highly electronegative elements like nitrogen, oxygen, and fluorine. It will exhibit hydrogen bonding. We see that most often in water. So we have hydrogen is slightly positive, oxygen slightly negative, and then it's going to turn itself in order for it to be the most comfortable to avoid repulsion and to be attracted to each other. It says on this that the blue dotted lines are the intermolecular forces. Those are the ones between molecules themselves. Hydrogen bonding affects the physical properties. It affects the boiling point. Let's go back to that slide. It affects the boiling point. So we have a high amount of hydrogen bonding happening within a water molecule. Now there's hydrogen bonding between hydrogen sulfide and hydrogen selenide and beryllium as well, but the big difference is the electronegative values of these elements. Oxygen is much more electronegative than the others, and you'll see a much stronger attraction to hydrogen's electrons, causing the hydrogen bonding to be much more in between the water molecules, and therefore you see a higher boiling point for water because it takes more energy, a higher temperature to separate the molecules in the liquid form, to separate them and get them away from each other to go to the gaseous state. London dispersion forces are instantaneous dipole moments that are going to occur accidentally. So every molecule, even a molecule that's diatomic that would have equal pull on electrons, is going to exhibit a London dispersion force because it's just an accidental occurrence that happens when you have a dipole moment happen in a similar atom that's next to it. It's significant if you have large atoms or molecules. It occurs in all molecules, including those that are nonpolar. So I have this instantaneous dipole moment, and the next thing you know, it kind of causes this shift in the one next to it, and then they develop a dipole moment. This happens in nonpolar molecules. Like I said before, we expect hydrogens to have equal pull on that electron, but this dipole moment can be caused due to a London dispersion force, and that induces the dipole on the second molecule. London dispersion forces are an issue depending on the size of the atom. So they're stronger as the size of the atom or the molecule increases because there's more protons and electrons to be reckoned with. So we have stronger dispersion forces, London dispersion forces in the molecules and atoms that have more electrons and protons. Melting points and boiling points. In general, the stronger the intermolecular forces, the higher the melting and boiling points are. So let's look at this concept check. And which molecule, or which of the molecules is capable of forming a stronger intermolecular force? So we decide that it's going to be the water molecule because there's hydrogen bonding between these molecules. We don't have hydrogen bonding between the nitrogen molecules. We actually just have a little bit of London dispersion forces going on. The answer is water. I'll skip over that one. Which gas would behave more ideally at the same condition of pressure and temperature? and why? So the one that's going to behave more ideally is going to be the nitrogen gas, because we know that ideal gases don't attract or repel each other. We have a dipole moment in the carbon monoxide molecule because of the difference in electronegative values. So there would be a slightly positive, slightly negative end on this. It's going to cause some attraction between molecules. The N2 molecule, other than London dispersion forces, shouldn't have any attraction to anything else around it due to equal bonding. Consider the following compounds: NH3, CH4, and CH2. How many of these compounds exhibit London dispersion forces? Because every molecule is going to exhibit London dispersion forces, all three of these, whether they have equal pull on the electrons or not, are going to have London dispersion forces.